Good evening, viewers and subscribers. Welcome back to another video. This is JK Engineering and Architecture coming to you again with another video. So in today's video, I am going to teach you how to calculate the bending moments diagram and the shear force diagram for a beam that has a uniform distributed load and a point load that is off center. In subsequent videos, I have reiterated to you that whenever time the load is not acting at the center, you cannot use the formula to calculate the maximum bending moment. So this video is to demonstrate just that. I am going to calculate the maximum bending moment for a point load as well as a UDL for a beam that has a UDL and a point load that is off center. So if you should look at the diagram here, to my left, this is the beam system that I'm going to demonstrate to you how to calculate the maximum bending moments and the maximum shear force diagram. So as you can see, this beam system, this beam, by the way, is a simple supported beam. And remember, I've stated to you that whenever time you are designing a beam, the first thing that you should take into consideration is the beam end condition. So whether the beam ends are fixed or whether the beam ends are uniformly supported. So are simply supported. So this is the beam here, right? So the beam has a 5 pounds per foot uniform distributed load from the reaction at RA spanning 10 feet. And 4 feet away from the uniform distributed load here is a point load of 10 pounds. So remember, I have stated to you that whenever time you are calculating the reaction for a beam with a UDL, the first thing you should do is to convert that uniform distributed load into a point load. So one thing I forgot to point out to you, that whenever time you see the beam has this symbol, this means that this end of the beam is hinged. So this end of the beam is hinged. And whenever time the beam is hinged, there are two reactions. There are a horizontal and a vertical reaction. So as you can see that the beam has a horizontal reaction and a vertical reaction. So that is for the end that is hinged. For the ends, for this end, the opposite end, which is on rollers, so this is a roller, you're only going to have one reaction. So if you should observe closely again, at one end we have the reaction A, and at the opposite end we have the reaction B. So what I'm going to do now, I'm going to redraw this by changing this UDL into a point load. So the beam is going to look like this. So this is the UDL. Sorry. So this here is the reaction at RA, the reaction at RB, and we are going to change this uniform distributed load into a point load. So if we are going to do that, the UDL spans 10 feet, so we're going to calculate the load and we're going to put this UDL as a point load at midspan between the center of this 10 feet here. So if I should do that, then we're going to have 5 pounds per foot times 10 feet. So we're going to have feet cancels feet, so we're going to leave with pounds. So we're going to have 5 times 10. So this is going to equal to 50 pounds. So our 50 pounds is going to come at midspan of that 10 feet. So we're going to have, and this is of course our 10-pound load. So we're going to have here as 5 feet, this as 5 feet, 4 feet, and 6 feet. So when I have converted the uniform distributed load here and converted into a point load, the beam is going to look something like this. So this is the beam system here. So the first step in plotting your shear force and your bending moments diagram is to find the reaction of your beam. So at the end to my left is reaction A, and if you observe, as I did mention to you before, that the beam, whenever the beam has this symbol, it means that this end of the beam is hinged, and there are going to be a horizontal reaction as well as a vertical reaction. But because the horizontal reaction is going to equal to 0, I am only going to concentrate on the vertical reaction of RA. And then to the right of the beam, we have the reaction of RB. So I have stated in subsequent videos that whenever time you are designing a beam, the beam must maintain equilibrium. If the beam is not in equilibrium, it means that that beam system is subjected to failure, right? So in order to calculate the reaction at A and the reaction at B, we have to sum our moments. And I did mention to you that to sum moments, we are going to sum moments that are going clockwise, and your clockwise moment must be equal to your anti-clockwise moment as well. So your clockwise moment must be equal to your anti-clockwise moment for your beam to be in equilibrium, as well as the summation of your forces going down must be equal to the summation of your forces going up. So your beam has to satisfy these two criteria. So to calculate the reaction, so I'm going to take moments at RA, and whenever time you are taking moments at any points or at either end, that particular position that you're taking moments must be equal to 0. So the summation of moment of RA is going to equal to 0 because that is where you're taking moments. So the summation of moments at RA must be equal to 0. Right? Let me write this a little bit better so that we can be clear. So it's going to be summation of moments at RA must be equal to 0, as well as your clockwise moment must be equal to your anti-clockwise moment. And the summation of your forces coming down must be equal to your summation of your forces going upwards. So we are taking moments at RA. So the first load that we are going to deal with is this 50-pound load here. And this 50-pound load here is acting 5 feet away from RA. So our first moment is going to be 50 pounds times 5 feet plus, and this 50 pound here is turning the beam clockwise, right? So the next load we have acting on top of the beam coming down is this 10 pound load here, and this 10 pound load is also going to turn the beam clockwise. So this 10 pound load here is acting 14 feet away from RA because the 10 pound load is right here. So we have 4 feet plus 5 feet plus another 5 feet, that is 14 feet. So we have 10 pounds times 14 feet. So we have taken care of our clockwise moment. So now we are going to look at what force on the beam is turning the beam anti-clockwise. So we are still taking moment at RA, and we have dealt with this 50 pound here and this 10 pound here. So the next load we have RB going up, and RB is going to turn the beam anti-clockwise. So it's going to turn the beam in this direction. So RB here is going to act 20 feet away from RA. So we have 10 plus 4, 14 plus 6, that is 20. So we have RB times 20 feet. We have RB times 20 feet. So we are going to calculate the reaction of RB. So in order to do that, we have 50 pounds times 5 pounds. So 55500, 5525. So we have 250 pounds foot there. Then we have 10 pounds times 14 pounds. So we're going to have plus 140 pounds foot equal to RB times 20 feet. So if we should add this 250 pounds plus this 140 pounds, we're going to end up with 390 pounds foot divided by 20 feet equal RB. See that? So we're going to divide this 20 feet, this 20 into this 390. So we have feet cancels feet here. So we are left with the unit of pounds. We have 0 cancel 0. And then we have 2 into 39, which is going to equal to 19.5. So 19.5 pounds is going to equal to RB. So the reaction at RB is going to equal to 19.5 pounds. Let me write this clear for all to see. So 19.5 pounds. So having calculated the reaction at RB, I now have to calculate the reaction at RA. So to do that, there's a shorter way how to do this, but I want to do it the long way so that if someone is watching and want to learn how to calculate moments, they can use, if they didn't catch it when I was doing when I was calculating RA, they can catch it when I'm doing the reaction for RB, okay, or vice versa. So we're going to take moments now at RB, and remember what I've said earlier, that wherever you're taking moments, that position is going to equal to 0. So we're going to have the summation now of moments at RB is going to equal to 0. Similarly to what we have done at RA. So we're going to take moments at RB now. So we're going to deal with this 50-pound load here. So this 50-pound load, if you hold the beam here and it's coming down, it's going to turn the beam this way. And that is anti-clockwise. So we have 50 pounds, and this 50 pounds here is acting 15 feet away from RB, because we have 5, the 50 pound is right here, 50 pound is right here, and it's acting 15 feet away from RB, because we have 6 plus 4 is 10 plus 5 is 15. So our first moment is going to be 50 times 15. So we have 50 pounds times 15 feet. Plus, we're going to deal with this 6 pound, this 10 pound load here, and this 10 pound load here at this point is acting 6 feet away from RB. So we have 10 pounds times 6 feet. Right? And then we have, so we have dealt with these two loads here, 50 pounds and 10 pounds respectively. So the only load that we have now going up is RA. And RA is going to turn the beam like this way, clockwise. So we have RA going up, and RA is acting 20 feet away from RB. So it's going to equal to RA times 20 feet. See that? So we're going to have 50 pounds times 15 feet. So we're going to end up with 5, 5, 25, 5, 1, 5, 1, 5, and 2, 7. Kind of over 0. So we have 750 pounds foot plus 10 times 6, which is going to be 60 pounds foot, divided by 20 feet equal RA. See that? So we're going to have 750 plus 60, which is going to be 810, because 810 pounds foot divided by 20 equal to RA. So feet cancels feet. So we are left with the unit of pounds. So 0 cancels 0, and 2 into 81, that goes 40.5 pounds equal to RA. So the reaction at RA is 40.5 pounds. See that? So now, since we have calculated the reaction of RA to be 40.5 pounds going up, and the reaction of RB, which is 19.5 pounds going up as well, we have 50 pounds coming down and 10 pounds coming down. Now, I have stated to you, and I have to reinforce this, that I think is the third or the second law of motion, to every action there's an equal and opposite reaction. So what that means is that the sum of the loads that are coming down must be equal to the sum of the loads that are going up. So we have the summation of forces coming down must be equal to the summation of forces going up for the beam to be in equilibrium. So let's check that out and find out if our beam is in equilibrium and in fact my reactions are correct. So we have coming down, we have 50 pounds plus 10 pounds, that is 60 pounds. And we have going up now, RA, which is 40.5, and RB, which is 19.5. 19.5 plus 40.5, that is 60 pounds. So I have just proven to you that my reaction is correct of 40.5 and 19.5 respectively, because my sum of my downward force is equal to my sum of my upward force. So we have 60 pounds here coming down is equal to 60 pounds here going up. So our beam is in equilibrium and our beam is stable. So now that I have done that, I can now move to calculate my shear force and my bending moments to get the maximum bending moments that is going to be needed to plug in the formula to calculate the reinforcement for this beam. Having calculated the reaction of RA to be 40.5 pounds, and the reaction at B to be 19.5 pounds, I can now move into plotting my shear force diagram and my bending moments diagram to determine the maximum bending moment. So in order to plot your shear force, the first thing you should observe is the forces that are going up as against the forces that are coming down. So the first load here, we have 40.5 pounds going up. We have this 5 pound per foot load coming down. We have our 10 pound load here coming down, and we have our 19.5 pound here going up at reaction B. So our shear force diagram is going to look something like this. So this here, sorry. So this line is going to be our x line, which is going to be 0. So we shear force on our plus sign, plus at the top, minus at the bottom. So the first thing we observe is this 40 pound, 40.5 pounds going up. So we draw our 40.5 pound going up. 40.5 pounds. And then now we have to calculate the load in between this 10 feet here that is pushing the beam down. So to calculate that load, as we did already, was 5 pounds per foot times 10 foot or 10 feet, and that equal to 10 times 5, that is 50 pounds, right? So we have 50 pounds at this point pushing down on the beam. So if you notice, so from this point here, which is 40.5 to 0 is 40.5. So that means we are only going down below the 0 line 9.5. So a 9.5 could be somewhere right here. So our shear force for the first point is going to look like this. So this point here is going to be 9.5 pounds. Right? So if you should observe that in between the 5 pounds per foot and the 10 pounds, nothing is happening in between here. So we simply carry this across. So we observe now that along this line here, 10 pounds is pushing down on the beam as well. So we are at 9.5 here, and it's going to push down the beam a further 10 pounds. So this point here is going to be 19.5, because 9.5 plus 10 is 19.5. So we go across here 19.5. So we have 19.5 here going up. So our shear force diagram is closed. So as I stated to you before, if you plot your shear force diagram and at the end here you're not getting the same value as your reaction, that means you have done something wrong. So if you notice, my 19.5 here comes back to my 19.5 right here. So that means my shear force diagram is correct. Now I am going to plot the bending moments diagram. The space is kind of limited for my bending moments diagram, but nonetheless I'm going to try. So our shear force diagram is going to be like this. So all this portion here is going to be the shear force diagram. But to plot the bending moments diagram, if you notice, even though we know that from this point here to this point is 10 feet, we do not know this point. We do not know the distance for that point here, for this point here. So we're going to call this point, the distance from here to here, x. Because we do not know the distance from here to here. And we need this distance to calculate the area of the respective shape to know the value for our maximum bending moment. So if you should pull the beam out, if you should project this line up, So this is our x value right here, which we do not know. So how to calculate x? I can just simply do this. So we have here 40.5 pounds going up, and this distance is x with a uniform distributed load of 5 pounds per foot. See that? So what we can do, we know that for the beam to be in equilibrium, this 40.5 feet, this 40.5 pounds going up must be equivalent to the same load that is coming down. So we can just equate this 40.5 pounds to 5 pounds times x. So we can do this. 40.5 pounds equal to 5 pounds per foot x. And we just merely solve for x. So x is going to be 40.5 pounds divided by 5 pounds per feet. And remember now, feet, pounds is going to cancel this pound here. It's going to cancel this pound, because remember now, this is pounds and this is pound over foot. So if you invert this to be foot over pounds, pounds cancel pound. So what you ended up having is feet. So 5 into 40.5, that goes 8.1 times. So it's 8.1 feet. So x equal to x. So x is equivalent to 8.1 feet. So the distance here, for argument's sake, I'm just going to roll it off to 8. So the distance here is going to be equivalent to 8 feet. Sorry. 8 feet. And if this distance is 10, that means the distance here is 2 feet. You see that? And then we have our 4 feet here, and this is our 6 feet. So to plot our bending moments diagram now, remember, I've said to you in numerous videos subsequently that in order to find the maximum bending moments, we have to find the area of all these respective shapes. So this area is going to be area 1. It's going to be area 1. This is going to be area 2. We're not going to calculate this area because since there's no load in between the 5 pound foot load and the 10 pound load. So we're not going to calculate this area, but we're going to calculate this area. So we're going to calculate area 1, area 2, area 3 to determine the maximum bending moment. So area 1 is a right angle triangle. So right angle triangle, of course, the area is half base times height. So the area area 1 is going to equal to a half times the base, which is 8 feet, times the height, which is 40.5 feet. Sorry, 40.5 pounds. So this is going to equal to 8 40.5 pounds. So this is going to equal to a half. A half of 8 is 4. 4 times 40.5 is 162 pounds foot. So our first area is 162. Our first moment is going to be 162 pounds foot. Now, area 2 is still a right angle triangle. So we have, it goes up 9.5 feet and the base is going to be 2 feet. So it's going to be a half times 2 feet times times 9.5 pounds. So we have 2 cancels 2, so we end up with 9.5 pounds foot. Our last area now is going to be the area of this square. So we have, it goes up 19.5 and the width is going to be 6 feet. So the area 3 is going to equal to 6 feet 6 feet times 19.5 pounds, and that is going to equal to 117 pounds foot. So just by looking at these figures, I can readily tell you that the maximum bending moment is going to be 162 pounds foot. So let's plot the bending moments diagram now. So I'm going to call here 162. So 162, because since it's a UDL, it's going to push down the beam like this. So this point here, from this point to this point, we're going to have a curve. Right? And then this area now, which is area 2, is 9.5 pounds foot. So we estimate that 9.5 comes somewhere there. So we have this curve up to this 9.5 here. Then our third area, which is 117 pounds foot, we estimate that to be some distance here above our 162. So we're going to come down to this point here of a 117, and then this is going to come to the end like that. So our shear force, or our bending moments diagram, our bending moments diagram is going to look something like this. Let me redraw it. So it's going to look something like this. So that is our bending moments diagram, and the maximum bending moment is going to be 162 pounds foot, which is going to be right at this point here. Right at that point. So I have come to the end of this video. I hope for those of you who have clicked on this video to watch the video until the end. In my next video, I'm going to be looking at fixed end moments. So if you're a regular viewer to this channel, you know what to do already. If you're new to this channel, please hit the subscription button. Please hit the thumbs up button and give me a like. And I am going to catch you in another video. Take care of yourself and enough respect. Thank you.